Okay, picking up with the next video, zoom back out here. So here we did the second derivative test, which is a nice kind of fast way to determine whether a critical number is going to lead to a max or min. And it would be good enough to graph. We didn't use it when I was graphing because first of all, when we're graphing, if we have critical numbers that come from the does not exist case, this doesn't work. And so the first derivative test, which works on all types of critical number, a little bit better when we're graphing. And the first derivative test is essentially when we made those increasing, decreasing charts. Now what the second derivative test is really good for is when all I want to know is, did you find a max or did you find a min? And again, you don't have the does not exist case here. But did I find a max, did I find a min? If that's all you really need to know, this is faster and easier. And this will be useful when we do optimization word problems. The concept of optimization is finding the best solution given certain real life things. You know, your best example is one of the best examples is the business world. Business world, they always want to maximize profits and revenues and minimize costs. That is an example of optimization. And many optimization problems talk about, profit and revenues and things. But optimization is about finding the best solution given all the constraints that you have. Can't give you an always that all problems work the same, just some general steps here. 1, read the problem and determine what quantity is to be optimized. Look for words like smallest, largest, biggest, maximum, minimum, fastest, slowest, etc. And that's how you will recognize optimization problems versus related rate problems. Related rate problems are always going to talk about things, a dynamic situation, things moving, generally with respect to time. Optimization problems generally aren't dynamic, things aren't moving, and it's always going to talk about biggest, smallest, largest, that sort of stuff. Draw a picture if applicable. 3, determine the constraints on the variables. Constraints are physical situations, real life situations that you must adhere to. One of the most famous type of problems, which we'll be doing first, a farmer building a field. The farmer in this problem is going to have 750 feet of fencing. That's my constraint. That's how much fencing the farmer has. 4, determine the quantity to be optimized and express this function as one variable. Also determine the interval of possible solutions. And we'll talk about that when we get there. 5, find the derivative and the critical numbers on the given interval. 6, test each critical number found for maximum or minimum status. If given a closed interval of possible values, use the procedure for finding absolute maximums and absolute minimums. B, if given an open interval of possible values, use the second derivative test. I am not going to be picky here. If you don't pick the best way to verify your maximum or minimum status, I'm not going to get upset at all. I'm not going to take off any points. But what I will take off points is for the vast majority of you that will not do step 6 at all. You will not test your answer for maximum and minimum status. The reason why you're not going to test your answer for maximum and minimum status is because the way they write Calculus 1 textbooks, and you're all saying, I don't have a textbook, I just have my math lab. My math lab has a textbook embedded in it. The way they write every single Calculus 1 textbook, you are going to get, when you find the critical numbers, you're not going to find critical numbers. You're going to find a number, because that's how they write Calculus 1 textbooks. And then it's always going to turn out that that number is the answer. Not because that's the way it has to be mathematically. That's just the way they write textbooks. In truth, when you find a critical number, all you have found is a possibility. You have found a possibility of a maximum, a minimum, or nothing. If you don't do step 6, you are saying my possibility, which I'm not going to bother testing, is guaranteed to be the answer, whether you wanted a maximum or minimum. That's not the way life is. And so you've got to do step 6 if you want full credit. Because mathematically, all you know about a critical number is it might lead to a local max. It might lead to a local min. It might not be anything. So if you don't do step 6, mathematically, you've proven nothing. Now, yes, the way they write the textbooks, every single time, if you did your work correctly, That's going to be the answer. But mathematically, you didn't know that for sure. So you've got to do step 6 if you want full credit. And then 7, answer the specific question. It could be that that critical number you found is only leading you to the correct numerical answer. So be sure you answer the question. Okay, first problem, a classic problem. A farmer with 750 feet of fencing wants to enclose a rectangular area, then divide it into 4 pens with fencing parallel to one side of the rectangle. What is the largest possible total area of the 4 pens? So I recognize it as an optimization problem because it talks about right there, largest possible total area. So I have read the problem. Step 2, draw a picture. Step 2, draw a picture. If you can, and we certainly can here. So a farmer is going to make a rectangular field, and then he's going to then he's going to divide it into 4 pens with fencing parallel to one side. So 1, 2, 3, 4 pens. There's my picture. Determine the constraint. Step 3, the constraint. The constraint is any physical situation you must adhere to, and so we have 750 feet of fencing. That's my constraint. So now what exactly is the fencing? The fencing is the sum of all of these line segments here. So I'm going to give some things, some variables here. X, 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 and Y, and Y. And just like when we did related rates, you've got to tell me what your variables mean. If you don't tell me what your variables mean, an X and Y are absolutely meaningless. This is good enough. Anybody that's reading this would know that X is all the vertical distances, Y is the horizontal distance. So 750 feet of fencing mathematically would mean this. 5x, each one of the x's, 1, 2, 3, 4, 5, 5x plus 2y equals 750. Then because I know what's coming up, solve for one of those variables. And that's the way it's just always going to be. We solve for one of those variables. It does not matter which variable you solve for. So I'm going to say 2y equals 750 minus 5x. So y equals 750 divided by 2 is 375. 375 minus 5x. Does not matter which variable you solve for. Just solve for whichever one seems to be easiest to you. So there's my constraint. Step 4, I've got to determine the quantity to be optimized. And so we want to maximize the area. And then I have to write a function in terms of one variable. So I look at my picture. My area is the area of a rectangle, which easy enough is x times y, but I need one variable. Except when we are doing implicit differentiation and related rates, we're doing single variable calculus. This is why, because I knew what was coming up, this is why I solved my constraint for one of the variables. Use the constraint that y equals 375 minus 5 halves x, and we get a equals, area equals x times 375 minus 5 halves x. Simplify, because you're about to do some calculus. Area equals 375x minus 5 halves x squared. So there's the function I'm going to work with. Now here's something that I'm not going to stress too much about. 4x on. If we're trying to be perfect as we're solving these problems, we're going to give an interval of possible values, an interval of what the answers might be, could be. These are almost always going to be physical situations. X is a distance, so negative numbers aren't going to make sense. Now, I'm going to start at 0, which from a physical standpoint makes no sense because that would mean that you don't generally work with distances of 0. I'm not going to stress too much if you put 0 or not. They're almost always going to start with, in Calculus 1 at this level, 0 is always going to be the start. Whether you decide to include 0 or not include 0, I'm not going to stress about that. The way it is usually done mathematically in Calculus 1 is if 0 will work in the function, meaning it's defined. I can put 0 in here and get an answer of 0. It is defined at 0, so mathematically they're going to accept 0. From a logic standpoint, you're building the fence, 0 would mean you're not going to build the fence. Now sometimes actually that's the correct answer to not build things, but like I said, I'm not going to stress if you put a square bracket or parenthesis there. But mathematically what they usually do is if 0 works in the function, they'll use a square bracket. If 0 is undefined in the original function, if the original function is undefined for 0, they'll usually put a parenthesis. So that's that one. So it's always going to start at 0. The second one, that's the harder one. That comes from your second variable that we need here, y. The secondary variable also needs to stay greater than or equal to 0. Again, not going to spaz whether you do the or equal to part. And so that'd be 375 minus 5 halves x greater than 0. Multiply everybody by 2. So that'd be 750 minus 5x is greater than 0. Negative 5x is greater than negative 750. And so x is less than or equal to, dividing 750 by 5, 150. And so there's my top number. And again, not worrying too much about the square bracket versus parenthesis thing, don't care. The first number is always going to be your primary variable, in this case x. It's always going to start near 0. Whether you put a square bracket or parenthesis, don't particularly care. Mathematically, what they go for, if the original function is defined at 0, square bracket. The second number is always going to come from your secondary variable, in this case y, and making sure that it too stays positive. Positive because all these things are going to be physical situations where negatives don't make any sense. So I want to make sure that my secondary variable is positive. Again, not going to worry about the or equal to. So y greater than or equal to 0. There's my expression for y. Get that? There's my other interval of values. So there's step 4. That's the hardest step. Finding my equation and my interval of possible values. If you can find the equation and that interval, you will be able to do the rest of the problem. But there isn't going to be an always here. It's going to vary from problem to problem to problem. But that's step 4. Find the equation in terms of one variable, find the interval of values. We'll conclude this lecture at this point and then finish the problem on the next one.